So, good afternoon. We're still in the afternoon, day 2, Cloud Expo, 9th Cloud Expo, Silicon Valley. Good morning, good afternoon, good evening if you're joining us out there on the World Wide Web. This is one of those great titles, isn't it, for a presentation? So I am fascinated what this session is going to involve. How to build an app with Twitter-like throughput, but this is new. The on just 9 servers has been added, I think. So I'm even more mystified. Let's let New Relic take the scene. They have 45 minutes to deliver on this. On board, gentlemen. Thunderous applause, please, for New Relic. Yes.
So originally, Lou, our CEO, was going to give this talk, and he's really great. He does stunts on stage, a little bit of acrobatics, keeps everybody entertained. But unfortunately, he had a family emergency, and so instead he sent 3 people to replace him. So hit the slide there, Nick. So I'm Bjorn. This is Nick, and we got Dave, and we have an interesting background. Now, Lou, who founded the company, started a previous company that did application performance monitoring, Wiley, that many of you might have used in previous lives, and then went on to do New Relic. I've done things like I worked at Amazon, I worked at the Eclipse Foundation, Nick worked at Motricity, where he kept servers running, Dave's worked at Salesforce, where they have some servers in clouds and things like that, but hit that button. But we're not interested in all that. Today we're here to talk about some interesting stuff about New Relic, but we're really not here to sell you the product, because you can go to our booth in the exhibit hall about that. What we're here is to talk about how we do Twitter-like throughput on just a few servers. So here's what we do. What we do is we do application performance monitoring. So if you've got a web application and it's out there and you want to know how it's doing, you put in our agent and it gathers some data up and reports back to us. Now, we do it as a service, so that means that we're collecting all this data from all of our customers all the time. We currently have about 250,000 applications reporting to our servers right now, at this very moment, from about 13,000 customers. And the fact that Nick's pager isn't going off at this very moment means that everything's up and running. Every one of those applications reports hundreds of metrics to our servers every minute. And we support a number of different languages. So the way we do this is, for each of the languages, we have a little agent that sits in that language, in that application. And like the Ruby agent is a gem, the Java agent is a jar, the PHP agent is a PHP VM extension, and so on. And it goes in and does bytecode instrumentation of your applications, picking specific methods and interesting features and things that are happening inside the application, gathers that data up, and sends it to us. So what happens? We collect 20 billion of these metrics every day from 250,000 different applications currently, 13,000 customers, and we do it all on 9 servers. Now, the question is, well, how can we do that kind of thing? And if you sort of think about what amount of data are we talking about? So if you go to the next slide, if you look at what the amount of data we're talking about collecting is, we collect some we call it time slice data, interesting bits of data at every minute about your application. So, we might say the response time from 11:04 to 11:05 was a certain thing. Each one of these bits of data is about 250 bytes long, pieces of data, which is, for the sake of argument of this talk, about the same size as a tweet. Now, it turns out, if you know anything about the way the Twitter API works, tweets are actually about 2,000 bytes long, because they have a lot of metadata that goes around those 140 characters. But let's just say, for the sake of argument, it's about the same size as a tweet. So if you look at what the maximum advertised tweet insert rate, let's see, I think it was the day that the United States killed bin Laden, that they said they got over 5,000 tweets per second on that particular day, and they had a sustained rate of over 3,000 tweets per second for 3.5 hours. This is public information that they've advertised. They may have had other days with higher throughput, like, say, the US Super Bowl. That's another big one. Or, I don't know, Kim Kardashian's wedding, for God's sakes, who knows. But anyway, that's the advertised data, is 5,000, 3,000 continuous. So let's just be generous and say that they put 2 rows into their database for every one of those tweets. So about 8,000 rows per second. We do about 7 billion rows a day of data into our databases. And if you do the math and you're sitting there with your calculator, that's about 80,000 rows a second of putting that data into that. And we do that on 9 servers. So that's the interesting part of this talk, is how do we do what appears to be 10 times Twitter's rate on just 9 servers, because you're pretty sure they have more than 9 servers. Well, The answer is we're not Twitter. You know, it's like comparing apples to oranges. They have a lot of interesting problems, and they have all sorts of interesting technology that we don't have, and they have all sorts of interesting problems that we don't have, and how to get that real-time information distributed across the whole thing. But we still have an interesting problem in the amount of data that comes in and the amount of data that goes out. So I feel like I'm just making you stand there. Press the slide button. Do you want to say anything?
I'm happy to oblige.
Okay, well, hit the slide button again then. So one of the interesting things about what we do is we collect a lot of data. I just said, you know, we collect 7 billion rows a day?
Yeah, about that.
About that, Dave says. On a good day. But we do more than that because people actually also want to see this data. It's not just collecting it, it's also reporting on it. And so, you know, our goal is to report on it in real time so that when your application has a problem right at this moment, you can see it at the next moment when you go and look at it. So that's real-time response. We want 1-minute granularity. The fact is, whenever you go to our website and look at your data, the page that you previously looked at is stale. So caching isn't going to help a lot in this particular solution. You know, Amazon caches lots and lots of things, and so they can serve up gazillions of pages on a relatively small number of servers, if you've ever seen how they do it. I mean, they have a lot of servers, but relatively small number, because a lot of the aspects of each one of those pages is cached. We can't really do that. And then, of course, every one of the users who comes to us and every account has a different set of data they're interested in looking at, because we don't want to show the data for Groupon to the people who come from, say, AT&T Interactive and are looking at their stuff. They want to see their own data, and so therefore all this caching and so on. The easy solutions that you might think of to serve that much data aren't going to work for us. So if you look at this next slide, you see here's the most popular page. It's your basic page about your application. It shows in this particular case, I think we're looking at our own application. The blue is how much time is spent in Ruby. The orange is how much time is spent in the database. And the brown at the bottom, the sludge at the bottom, is the garbage collection time in the Ruby. And there's some other things on there. But the thing is that every one of these pieces of the page, hit that slide, is another query to the database. So to get the data for that 30-minute chart, we have to query the database for those particular metrics. To get the data for the chart of throughput, we have to query the database. To get the events, interesting events that have happened, downtime, uptime, slow response time, another query. For slow transactions, another query. For errors, another query. And then to break it out by which machines are responding fast or slow or have problems, yet another query. So every one of these things is a separate query. So there's an interesting challenge in all this querying we have to do to generate each one of these pages for you. And our current page time is about 1.8 seconds for each one of these pages. So we're doing pretty well in inserting 7 billion rows into the database every day and then querying it out for all of our 13,000 customers at the same time. So, Nick.
Bjorn.
Or Dave.
Yeah, so the software stack that supports this kind of data throughput is pretty simple. We've got sort of 2 main components. There's UI, obviously, that Bjorn was just showing you. That's just a standard Rails application. There's a REST API to it. You know, kind of standard stuff there, Rails 2.3. It sits on a couple servers. You know, there's nothing too out of the ordinary there. It's pretty common, just run-of-the-mill Rails application. The collection tier is sort of a custom-written Java application. It just uses embedded Jetty server to handle a HTTP request. And it's got a thin little layer back to the database, which is a MySQL store. So on each of the data servers, there's a MySQL instance, and then there's this collector process instance. And that collector kind of gathers that data, buffers it up sort of over a minute, harvests it out, writes it out to MySQL. And that's the main flow, that's the main application components there. So the simplified architecture, yeah. So
this slide works better if we can point to it.
Well,
so
here,
Nick, if you run over to that slide, and I'll run over to this slide.
Right,
he's actually going to do it. This is great. See, this is your entertainment for the day.
On the far left, you have the customer's environment. So as Bjorn mentioned, this is a software as a service application. We have an agent that sits in process in the customer's application server on their servers or their virtual machines, however they have it organized. That's sending data to us every minute. Each one of those agents sends us that chunk of data. That comes in through our load balancer, through our firewall, and lands on one of these collector aggregator sort of database tier servers. We call it our data server, and it runs the combined collector stack and Java stack.
Here's where one of our advantages comes in. As Bjorn said, if you're Groupon, you don't want to see AT&T's data. If you're AT&T, you don't want to see Groupon's data. So we are able to shard our database vertically very cleanly based on customers. So it says non-collector aggregators. Each one of those serves a subset of the customers. So we don't have to make on-the-fly determinations for where your data is or replicating it from one to the other. We have this very natural fit of sharding with our architecture.
As long as no one customer is over 1/9 of our customer base, then we're great.
Yeah, so that's the weak part if you want to look at it that way. We have to have a server that's at least as big as our biggest customer. And so far, that's been OK. So that's the collection side. And then the UI piece, there's 2 more servers that just run the UI stack. And so it's like the typical Rails app.
So not only do we have the 7 billion rows of data from the applications, we also, what was it, last spring? Last June, added real user monitoring to the application. So we had application monitoring, and then we went up the stack so that we also monitored at the real user case. So we put a little JavaScript in your output page. It calls back to a beacon, tells us how long the network time is for each of your actual users who are using your application. So the browser reports back to our beacon servers, aggregating more and more data, and we're monitoring at the moment about 3.5 billion page views per week on this beacon server. And so this doubled, when we first launched it, it doubled the number of incoming HTTP requests we had right away. So we had to have sufficient headroom on our servers to accommodate that. And this is how the architecture of the beacons works.
So maybe I should jog back over there, but
jog right back over there, Nick.
The key piece of the beacon architecture is if you want to do about 450,000 requests a minute, and we're doing this actually on one server, you have to do less. We don't have a fancy architecture for dealing with the beacon data. It's very straightforward. The HTTP gets come into our system. It's, again, it's Jetty. Dave can speak more on kind of the tricks involved in getting that to work properly. Then these requests are pre-aggregated in memory on this system and then reported for every account once a minute back to our existing data collectors. So we've turned this 450,000 requests a minute down into 1 request a minute per account that goes into all the way into our data backend. So doing less absolutely is the key to kind of why we say, we look at our collector numbers and our time slice numbers, and they don't include this extra 3 billion page views a day.
And you'll see in another couple of slides here that one of the tricks to serving this much data input and then this much data output on a system with this few servers, I mean, 9 servers is not a lot of servers, is choosing what to aggregate and what not to aggregate. Because of course you can't collect all the data all the time, but in the other case, every one of you who's out there using the product actually wants to see basically almost all the data all the time. And so the question is, where do we do that aggregation? And now, just to make things even more difficult, we've added yet another layer to the whole thing, collecting even more data. So we're now collecting data from your server layer, your application layer, and your real user layer at the top.
So in comparison to the real user monitoring beacon task, the server monitoring task is relatively easy from a data collection perspective. The server agent runs as a piece of software on each server in your environment. So if you have 200 servers, that's 200 HTTP posts every minute. That's not that terrible for us in the grand scheme of things. And the number of metrics coming through is relatively small also. So a server has a finite set. It wants to talk about the CPU, wants to talk about the disk, and we talk about processes. So we're talking maybe 50 metrics on each post from a server, as opposed to a web application, which could have hundreds of metrics and large data blobs like transaction traces and errors. So the server monitor is great functionality, and the agent required a little bit of work to get it right. But from a data collection perspective, it doesn't add a lot to our total number.
Okay, so we're not going to ask Nick to talk anymore because he's not making it sound spectacular. Because see, it's like lots of data, Nick. That's the story. Lots of data. Okay, so what's the challenge to lots of data? Well, there's a few challenges.
Yeah, so as you can imagine, sort of citing these numbers, just kind of do the math on how that starts to add up on disk, that starts eating up a lot of disk space very quickly. So we've got to like churn through that and throw it out periodically. You know, we've got different retention policies based on subscription level, like a week to 3 months sort of thing. If you've ever sort of worked with MySQL, like doing a massive like delete from on a table, that's not going to go very far. So we've got to just like drop the tables out piece by piece. And that has its own problems in MySQL if you have on older versions. So we've been sort of doing a lot of tuning there, making that process work kind of smoothly so that we can take all this data in, persist it, free up room for more data coming in later on.
And part of that is deciding what to purge when, right? Because, for example, one of the things you want to see is you want to see the data about what's happening on your servers right now in very great detail, but you probably don't want to see the data about what happened on your server 6 months ago in as much detail. So one of the things we choose to do is we prune the data as it goes historically old so that we store less and less data in, or aggregate it into larger time chunks.
Yeah, that's true. So this minute by minute data is coming in, that's getting stored. We roll that up into sort of hour-wide chunks. And if you're doing data queries like over a week, say, hour by hour is plenty of granularity. The recent data you want to see right now, sort of that minute by minute is kind of what you want. So we bucket the data into those two groups, like the minute-wide resolution data and the hour-wide resolution data. And we sort of flow from one resolution to the next and then sort of purge it out as it goes that way. The other challenge with this sort of thing is using large accounts. So we have an amazing kind of data skew from our free accounts, well, not necessarily free, but like some accounts don't send us that much data. There's like a small number of agents, a very lightly used process, or there's very large customers with many, many hosts, many, many applications, send us tons of data. We talked about the sharding architecture earlier, like, all right, well, that's set up when the account's created. So that, you know, we make that determination then, but we don't know at that point whether that's going to be, that account's going to be sending us a ton of data or a very small amount of data. So what we end up doing is we just kind of monitor that over time. We sort of rotate which shards are accepting signups sort of as time goes on. It's a very manual process. We kind of scan it every few weeks. New signups should go there, other signups should go there. The large accounts, if they get really big, we try to work out ways to kind of split those into sub-accounts so that we can then have portions of data live on one shard versus another, and so we don't have to have one server that's as big as our biggest account. We're sort of working on ways to avoid doing that.
And one of the things about the pre-aggregation, which is interesting, is, again, going back to our title of the talk of comparing ourselves to Twitter, because we're just that good, Dave, right? Is that, you know, one of the things we do is as the data comes through our collector tier, we do some pre-processing on it so that our queries can be less intrusive on the database on the back end. And so we've looked at in our user interface what sort of things people are busy looking for when they fire up that page and they drill down. What are the interesting data that they're always looking for? And we pre-compute that as it flows through in a stream computation instead of just doing big SQL queries for all of that stuff. It would be sort of like in Twitter if we pre-computed common hashtags, and as the data flew through, you would aggregate, I don't know, something about how often that hashtag appeared and showed it. And that's sort of the type of pre-aggregation we're doing.
Yeah, sort of like the point metrics, just a number. We compute a lot of that ahead of time over about a 3-minute window, and then going into a time series graph. That's when we have to actually go back and query these other tables over time. And so we put a lot into that sort of pre-aggregation, pre-tuning, stuff like that. Another challenge we have then is the I/O performance that sort of comes along with all this. We're writing out tons and tons of data. This is using MySQL and InnoDB. There's a lot of sort of churn through InnoDB's buffer cache, writing to the disk. And we end up, you know, we now have the server monitoring product that we sort of added on. It's given us sort of great visibility into how exactly MySQL is beating on the disk. And that's now given us some insight like, all right, well, we need to kind of get this data off of these spindles, or maybe move this data onto another volume altogether, things like that. And so this has kind of opened up new things for us to start to look at in terms of tuning the system by sort of realizing that we're actually becoming I/O bound on these 9 servers. Like, all right, well, with some clever tricks here and there, we can move some of that I/O around and then get more life out of these servers. So, Nick, I think move on to the next here.
So we thought we'd try and aggregate this interesting equivalence to Twitter to 5 lessons that we've learned about building a company like this, doing this much, 7 billion rows of data a day. all at once into 5 simple lessons or easy lessons, okay? And the first one I would say is just keep it simple. None of the stuff that we write is particularly complex in the software architecture. We don't need PhDs in computer science to write this stuff. Let's see, it's just basic, straightforward the way you'd see it. Now, that doesn't mean that it's not difficult to write, because you need to spend some time finding out exactly where your performance problems are, because some of the things, like let's say you had a large account with, say, what's our large accounts, like 2,000 servers reporting?
Yeah, it's probably on a big side.
So if you had like 2,000 servers reporting and you make a drop-down list that you can select any one of the 2,000 servers, just simply populating that drop-down list is going to take quite a long time for the user. So you have to do some tricks, and you have to look at some of these things that aren't necessarily obvious at the beginning in writing the software. But again, the software isn't particularly complicated. Dave was showing the architecture earlier. We're running on Jetty. We're running on Rails. We're not even running on the current cutting-edge version of Rails. We're running on an older version of Rails. We're running on top of MySQL. None of that is particularly spectacular, magical stuff. So if you keep it simple, then you can understand the behavior of your system. And our system we have never had a problem where it sort of does something and we don't understand what it's doing. We've had problems where it does something and we understand what it's doing and it's not the right thing, but we haven't had the problem where we don't know what it's doing. So, and the advantage of that is we've kept it very simple. Another one of the lessons is that sort of less is more. And in this case, what I'm talking about is having fewer people work on the system. So our engineering team is about 30 people right now, serving 7 billion rows of data a day, 13,000 customers. It's not a lot of people for an engineering team. And that includes operations, that includes the IT support staff, includes the developers on the front end and the back end in all 5 languages. So one of the advantages of having a small team is that you don't have a lot of different ways of communication. You have these problems of communication if you have, say, 100 people on a team or 200 people on a team. We've all worked at large companies where there are like 1,000 developers working on some project, and you spend all your time in meetings and you spend all your time writing requirements documents and things like that. And our philosophy here at New Relic was just, let's get a bunch of smart people in the room, and many of them are here on stage today, so they're not actually working. And then let's see what we can do with just a few smart people building some cool stuff. The third lesson we've got here is that the trendy hot thing isn't necessarily a reliable thing. Again, the software stack that we've chosen is really simple and straightforward, right? We're not using the latest fancy
there's no queues, there's no Hadoop, there's no anything fancy that you've probably read about in a blog in the last year. I mean, it's the retrogrouch software stack, but it works. It's very simple, and it's served us well.
And so it's not Lady Gaga of software. This is the like the Beatles of software. It's like the really simple base. But it reliably, we deploy our software at least once a day. Customers don't even notice. In fact, Nick was demoing last night at the exhibit hall, and we were releasing a new version of the software, and he happened to see the deployment line go by on the screen and said, "Oh, it looks like they've deployed up there in Portland," and he didn't even know it happened, right? And we can do that because we have just basic, simple stuff. At the same time that I say, we should do the basic, simple stuff, you have to plan ahead if you want to grow to a big company. So one of the things that Dave talked about is that we got a sharded architecture. And we planned early to do sharding because we wanted to be big and we wanted to be a fabulously large company. When we first started, we had just a few customers and there was no need to do sharding. But we put it in the very first product so that we could grow it rapidly as we acquired more customers. So it's one of those architectural decisions that you need to make early on to do things like that. So you got to plan for scale, even if you don't currently have scale. Doesn't mean you need to use something fancy like Cassandra or Hadoop or something, but you do need to plan for that. The other thing that we did, which in retrospect turned out to be a great thing for scale, but we didn't actually put it in for scale, we put it in because networks are unreliable, is that when the agents report back to our collectors, if they can't get a hold of the collector, they just keep the data for the next time they try. And so if the collectors get overloaded, the agents all sort of scale back in let's see, what's the term in TCP/IP where it's collision?
Yeah, sort of is.
That. Where, as it collides and the performance goes down, the agents start reporting less often, but keeping all the data so that when they report, they just report a little bit larger version of the data. But this way we can, for instance, roll out a new version of the collectors and none of our customers out there notice because all their agents just kept the data for an extra minute and then reported it. And as long as we have sufficient headroom on the collectors, we can handle that kind of turnover. And that's another one of the things that we built. Now, again, we built it because we knew that networks were unreliable, but it also helps us for scale because if the collectors start to max out, then the agents don't take it down, right? Which is one of your common problems.
Just take up some of that slack from the network, from the customer environments.
Yeah.
As well.
Now, we've managed to take ourselves down. But, and then the fifth one is, and actually, if you look at these 5 points, they're all the same point. But I've broken them up into 5 points because it sounds better. And the fifth one is, use the right technology for the given task. So again, we use very simple, straightforward technologies for these things. We use very simple, straightforward architectures in the way that we've built the application. And so this is how we're able to collect 7 billion rows of data into our databases every day, and they're not melting down. Now, I think that those servers are like water cooled or something, right? There's like a guy with a pitcher of water pouring it over the disk.
They're off the shelf. They're very normal.
Mid-range hardware from Dell. It's nothing really special.
So with the appropriate technology, you can do that. So we're happy to answer lots of questions. Dave will answer the hard ones. Nick will answer the medium ones, and I'll answer the easy ones. That's why there's 3 of us on stage. And we also have a booth out in the exhibit hall, and you can watch us monitor ourselves. We have New Relic monitoring New Relic out there, and just look for anybody with the official New Relic uniform on, and they can show it to you. And the guy with the microphone.
The guy with the microphone. Here come the questions. I think you should, if it's a difficult one, insist that he answers, all right?
So I'm going to ask you a simple question. You said that you used 9 servers, right? So why is it 9? Why can't it be more, or why can't it be less?
It started out as, I think, 3. So we started out on a managed infrastructure layer. So this was like typical cloud kind of incubation thing, and it didn't really have the best performance. So we split things down.
Well, that's not true. Especially, Dave, since you're standing at the Cloud Expo. You actually have to say the right thing, which is...
Oh, yeah, security's going to come haul me off now.
It did have the right performance, but as we outgrew the 3 servers,
it had adequate performance, we'll put it that way. So we ended up sort of breaking things down faster than we normally would have with sort of bigger infrastructure. And part of that was just managing that growth, and then part of it was also, well, we're doing maintenance here, we only want to impact some portion of customers at a time, and we sort of just arbitrarily chose 1/8. So we went from 3 to 8 pretty quickly, thinking that, like, all right, we don't mind bothering 12% of customers at any given time. We were sort of pushing up against some limits, like, well, let's bring on a 9th one here, and that's sort of where we've been. So that's the evolution from 3 to 8 to 9.
And then, we expect that as we get more and more customers, we'll eventually add a 10th server and an 11th server, but we still have sufficient headroom on these 9, so it's not a problem.
So you talked about Twitter, right? I mean, that was really great. So does Twitter is going to use your service?
Pardon? Could you repeat that?
The Twitter, you gave me a good example of the Twitter thing, the messages coming in. And so my question is, like, does Twitter really need your service, or are they using your service?
Not that I'm aware of, but if somebody from Twitter is in the audience, they could speak up about that.
Okay, thank you.
Questions from further back here. Here we go.
Can I ask 2 questions? I'm going to ask 2 questions. My first question is, well, actually, first I want to say before I ask a question, I want to thank you for, so openly sharing your architecture. Actually, this is the first talk I've heard at Cloud Expo where there was actually some interesting technical material, and I wasn't just hearing a sales pitch.
Thank you.
My first question is, I mean, I understand you very clearly why you try to be as efficient as possible in terms of use of your servers and the benefits you've gotten out of that. A very small, tight technical team, and which makes for rapid development, rapid iterative development, and community.
So you're going to have to move the microphone closer to you or speak up a little bit.
I'm sorry. I'm sorry.
We're having a hard time hearing up here on stage.
I'll repeat that. So my question is, I think I understand very well why you've worked so hard up to a point in being so efficient in your use of servers. And what I see as real benefits is, as you said, and correct me if I'm wrong, is the primary benefits are actually essentially keeping a small, very talented engineering team. And by doing that, you're much more agile. You can move much more quickly because you basically have a small group of very bright engineers who communicate very well with each other, and you get the turnaround. So given all that, but at some point it sounds like I get the feeling that you're becoming somewhat successful.
We hope so, because we've managed to buy these fancy jackets.
Yeah,
right?
okay.
Hands off my jacket, man.
If we fail as a software company, we're going into fashion.
The puzzling thing I have is at a point, and I would imagine if you continue like this and you provide the kind of service that you're providing, which looks extremely valuable, you're going to be generating a lot of revenue, and you're not saving much money. I mean, hardware, it's so cheap.
So I think.
I mean, why concentrate? So my question is simply this: why are you going to continue focusing on?
There's two answers to your question, or maybe two answers to the question I think you're asking. So the first answer is, why do we keep a small software team? And the reason we keep a small software team is because it's more efficient than having a larger software team.
No, I understand that.
The other interesting answer. Hang on.
So few servers when servers are so cheap.
But hang on. So the other interesting fact is by having a small data packet from the agents. So for every one of these agents we've stuck in every one of our customers' applications, we want to keep that data packet as small as possible coming out of their application and going into our application. And not only is that to our advantage because it's less data we have to process, but it's to the customer's advantage because then we use up less of their bandwidth because we're software as a service, right? So we don't want to use up a huge amount of the customer's bandwidth just for monitoring purposes. So you want to keep things small. You want to keep things small both on the engineering team. You want to keep things small on the data side. You want to keep things small but very useful.
And I think to address the more general question of, is it worthwhile to focus on server efficiency when you can just buy more servers, you can just throw hardware at it? It's a matter, in many ways, of discipline. It's if you focus on the performance, if you focus on keeping a system simple that you can understand and you can debug, it's not just it'll take less servers to run on. It will be easier for you to understand when it breaks. It will show you the problems earlier before they become a big architectural issue. It forces us to make the right decisions as we're building our software. Now, as we grow, we'll have more servers. We're not going to be 9 servers forever. We'll come back and give this talk. Next year we'll have a bigger number or something. But the process of staying efficient is what's important.
No, Nick, we're going to stay with 9 all the time. We're just going to change the base of the radix. Yeah, exactly.
No, another question. Let's move on. Another question.
Well, look, let's talk afterwards.
I have a quick question. The choice of MySQL surprised me. I mean, I know historically there's been a lot of trouble with locking on the tables and stuff. I mean, can you kind of give an indication how you may or may not have got around that?
How can I say this delicately since Lou's not here?
I would say we chose MySQL because it has fewer letters in the name than PostgreSQL. But,
no, it was the default choice for Rails. And we started the company as a Rails app, and what do you use? Use MySQL. And we just sort of stuck with it and figured out how to make it work. And we sort of encountered these various issues as we've gone. And so far, we've had great help from Percona, actually, in working through some of these issues. And at this point, it would be more effort to change to something else than to just continue working through the issue with MySQL. That's sort of how we feel. And so it wasn't that we sat down at the beginning of the company like, all right, well, what's the very best choice for all these different pieces? Like, well, what makes sense right now? And what made sense to Lou when he started the company was like, I'm going to make a Rails app, and everybody uses MySQL, so that's what I'm going to use.
Well, and so what we've done is we've chosen to replace the pieces of our architecture where they start to break down. So originally our collector aggregator tier was a Rails app itself, but we were starting to have performance problems and throughput problems on there, so we rewrote it as a Java app to take advantage of the JVM being a little more efficient than the Ruby VM we were using at the time. So if we ever come to a time when the MySQL database is actually causing us problems and is actually the source of our problems, we'll replace it with some other database, but there's no point in doing that yet because it's working fine for us.
Thank you for your presentation. I get a question about your sharding. How are you doing the sharding right now? Is it automatic sharding or you are manually sharding? And what factors are dependent on it?
So the sharding is assigned when a new account is created. We have a set of shards that we consider to be open for business for new users. So when a new user account is created, we just assign it automatically to one of those shards. And that's now your home for your metadata forever. If after a while turns out you have a runaway success app, you have a lot of data, we want to move some of your data off to another shard, we can redirect your metric data, all of the time slices that we talked about earlier, to go to a shard that has more capacity. But we took a really simple approach. We just said, at account creation time, you just get assigned one for your account, and that's just where you stay. Requests coming into our system come down to a component, our collector proxy, which assigns them back out to their correct shard. So if you go to collector.newrelic.com and you belong on the shard number 3, then you'll get a redirect to say, hey, go back to collector3.newrelic.com. And then all future requests during that session will just go directly in to the destination shard without a need to go to any centralized point.
I had a question about your data pruning. Can you describe or indicate how you came up with when you do data pruning? And a couple more questions. When you do the data pruning, do you have customers that desire the data to be artifact in any way once you've decided to prune off the data?
So we sort of came to where we are in the data pruning. Like, we've evolved sort of the product and subscription levels, and that sort of sets at least one parameter. The free accounts, we don't keep that data around very long. The higher level professional accounts, we keep that around for 3 months, and there's sort of the granularity that I described earlier on that.
The other part to that is that, for the free accounts, we keep it around for just a little bit because it's a free account. For the longer term accounts, we keep it around for a longer term, but we prune it from minute data to hourly data based on the use cases that we've watched our customers use. They say, here's the sort of things we want to use your application for, and we go, oh, for those sort of things you need this kind of data at this time frame. And so then we've tuned our data pruning strategy to match what the users are using the data for.
Is that?
So the question.
I didn't know what do you do anything to permanently archive something once it's pruned?
So the question is, do we permanently archive any of the data after it's been pruned?
No, we don't. So we have offsite backups of that data, but then it sort of gets pruned on the same retention policy. Like you were asking about if customers requested that. Like, we have an API so customers can retrieve the data if they want their own personal copy for some reason. We kind of discourage people from doing that all the time because that's a much more load, and we've built the best app for viewing this data, so why do you need it? Wrong way to look at it. So no, I mean, there's no sort of permanent storage that we have built in as anything like that.
So the answer to that is I'm going to claim even more nuanced because I'm wearing the nicer shirt. So we keep some of the data around for a very long period of time. So if you're one of our enterprise customers, your data is kept around forever. But not all of your data, just the data that's interesting to be kept around forever. And the data like your server went down at 11 o'clock this morning, came back at 11:02 this morning, we don't keep that around forever. Right, so in addition to we prune the data, we've also tailored that pruning to the use cases that the customers have.
Here we have.
Yeah. So it's interesting that you're using 9 servers and the fact that you've been able to cut your cost. But have you gone through the motions if you lose these servers? What's the implication on the customers? How long it would take you to get it back up?
We have that, and we have a number of, actually, we have hot spares sitting around, so we actually own more than 9 servers. We're just not using them all. And we have backups and ways to transition from one to the other and to get the new server up as quickly as possible, and so it can start showing you the immediate data and then bring the older data back from the backups as fast as possible. So yeah, we actually have more than 9 servers sitting in the closet.
How did the company come up with its name?
An excellent point. Let me go back to the beginning here. So New Relic, New Relic is an anagram of Lou Cerny, and that's how he came up with the name of the company.
Another one here.
Just a question on cookies. How many cookies does New Relic store as part of the agent?
How many what?
Cookies.
Cookies?
Yeah.
Well, if you have the real user monitoring stored, we have one cookie on your browser. And if you are just using application monitoring, we don't have any cookies at all. Because the application monitoring agent is part of the application, it's not a client browser side thing. It's actually in the application itself, like a gem for Ruby or a jar on the Java side.
Okay, thanks.
Can you please describe your security approach?
I'm sorry, the sound up here is actually, I'm hoping you can hear us because the sound up here is lousy, so you'll have to say that again.
Okay. Can you hear me clearly?
Say it again.
Can you hear me?
I can hear you now.
Okay, can you please describe your security model approach?
Oh, the security model.
Yes, please. At
Dave.
different layers.
So the security model, so by default, our agent is configured in such a way to not send us extremely sensitive data. And we work very closely with our customers so that they understand how the agent works, what kind of data it collects, how it's transmitted to us, because a lot of them, various enterprise customers are very concerned about that, obviously. And we kind of work with them and to kind of come to an agreement that, yeah, maybe this actually isn't the most sensitive data they have, and given the visibility that our tool enables, it's sort of worthwhile to take on the risk of sending some aggregate performance data to us. Once it gets inside, I'm not going to go through all the details. This is sort of the customary, industry best practices around things. We're a small company. We haven't yet sort of bitten off the whole certification regime thing yet. We sort of work towards those principles, but we don't have a formal audit on those principles yet.
So,
thank you.
For example, the data that we collect is aggregate performance data. For instance, if you had a site that collected credit card payments, the credit cards aren't come to us. The only thing that's coming to us is that the page that the person enters the credit card on takes 500 milliseconds to generate, of which 200 milliseconds is database time and 300 milliseconds is Ruby time, and the Ruby time is broken down into blah, blah, blah. But never was the credit card data actually sent over, right?
Okay, I can see that you are now competing with the opening of the show floor. Can you see those defectors there? So perhaps we should release, they know we're serving food. That's what you're up against.
I know they're all going over to our booth to learn more about New Relic. So thanks.
Let's give up thanks to Björn.